Hi everyone, my name is Sergio and today we're going to see what would happen if the Earth got hit by a black hole. Spoiler alert, we all die. Okay, so first of all you should be asking me, how do you know what's going to happen if a black hole hits the Earth? And that's a very good question. I mean, we don't have any data of that. I mean, we cannot observe such events. Maybe you've seen this picture before. This is the first picture ever of a black hole. But this black hole is sitting in the center of a galaxy and, well, it's not interacting with a planet whatsoever, or maybe we cannot see it. So the question still remains, how do we know what's going to happen? And the answer is, well, we run a simulation. And what's a simulation then? Well, glad you asked. Let's see it with a simple example. Okay, let's go to the computer. Let's say we have a box, and now I'll place two particles inside this box. And what I'm going to do now is I'm going to compute the gravitational force between these two particles using Newton's gravitational law. Very simple. Now, once that's done, I'm going to update the positions and the velocities of these two particles using the force I just computed. And I know that was difficult to see, so I'm going to do it again. I'm going to compute the gravitational force between these two particles, and now I'm going to update their positions and their velocities according to that force I just computed. Now I can do this over and over and over again, and this is what I get. Let's run another one. This time I'll have the same two particles again, but I'll add some initial velocity in the horizontal direction. Let's see what happens. One last example. Let's put four particles in the vertices of a square like this, and I'm going to make one of them 10 times more massive than the rest. Let's see if you can figure out which one it is. Okay, notice that depending on the initial positions and the velocities of the particles before the start of the simulation, we get very different outcomes. These are called the initial conditions of the simulation, and remember that because we'll come back to that later. These examples of simulations were quite simple because the only bit of physics involved was Newton's gravity. But depending on the problem you want to tackle, you may want to include new physics. For instance, if you want to study galaxies, you may want to include dark matter, for instance, or supernovas. The point is that any bit of physics can be included into a simulation if you need it. For our particular case of a black hole hitting the Earth, we want gravity in our simulation, obviously. We want hydrodynamics, which is basically the force responsible for the Earth not falling into itself due to gravity. And we also want to code the event horizon of the black hole. As you probably know, anything falling into a black hole does not come out, so we want to have that in our simulation. Okay, now we know how to run and build simulations, so we're going to do it with the Earth and the black hole. But first, I'm going to show you the initial conditions. Remember those? Those are the positions and velocities of my particles before the start of the simulation. Let's take a look. Okay, so here we are in our simulation box. And, well, you can see at the center this black particle, which obviously is going to be our black hole. And we have here orange and blue particles, which represent the Earth. Now, orange particles represent granite, which is basically what the mantle of the Earth is made of. And blue particles are iron particles, representing the core of the planet. Now, another thing to mention is that the mass of the black hole is 100 times bigger than the mass of the Earth. So all those particles here, the sum of the masses of all those particles here are just 1% the mass of this particle. So enough talk, and let's see what happens. Well, that's not looking great for us, but it was quite fun, so let's watch it again. A few things to mention here. First of all, don't worry too much. The chances of this happening are extremely low. Second, the simulation takes only 1 hour from start to finish. I'm using 100,000 particles, and you can only see here 10,000 on screen because my graphics card would explode otherwise. This is a lot compared to the 4 particles we saw at the beginning, but it's not much compared to the 10 to 100 million particles we normally use for simulations of giant impacts between planets. The idea is the more particles, the better resolution. Now I would like to go back to the simulation box at certain times of the simulation. So let's go back into it. This is how the simulation box looks exactly at 15 minutes from start. And I think it's quite amazing to see how the Earth, or the planet, gets stretched like this due to gravity. The point here is that gravity near the black hole is much, much stronger than here, for instance. That's why we get this funny shape. This would be quite an extreme case of tidal forces, but the idea is the same. Another interesting time is 1 hour after the start of the simulation. That is the end of the simulation, basically. Here we can see the outcome of the event. A lot of particles have ended up inside the black hole, but we cannot see it for obvious reasons. Some particles have ended up orbiting the black hole in what we call an accretion disk. And finally, some particles were lucky enough to escape the first encounter with the black hole, forming this cloud of material around here. Now, some of these particles will ended up again in the black hole, and some of them will escape, depending on the velocity they have at this point. A way to figure out which ones would survive is just to run the simulation for longer. Okay, now what? Is that it? Well, not really. This is just half of the story. We run these simulations to make predictions of what would happen in the real world. So now it's time to go out there and test our predictions with real data. We cannot do it with the current technology, but imagine for a second that we could go out there and get the data we need. Now, 2 things could happen. The first one is that, your predictions match the data. Good job. You get to publish a paper. The second one, which is far more exciting, is your predictions do not match the data. That means our physics are wrong. Did we miss something? What's happening here is that there is a piece of physics we didn't include in the simulation in the first place. That's why our predictions are wrong. Meaning there are new physics to be discovered, and nothing makes us happier than new physics. Okay, maybe free food in the department, but other than that, new physics. Well, that was it. I hope this was fun and entertaining and that you learned something new. If you're watching this on YouTube, you could live a life. That way you're telling the government that you care about science and nothing else. Thanks for watching.